نوقف هنا. انا اليوم ما حتكلم كثير في الشرح لانه already we've been through اغلب الافكار حقت الدرس اليوم. اليوم ان شاء الله we will end chapter 11 and اللي حاسس نفسه ضايع الحمد لله انه chapter 11 كامل الان له فيديوهات في البلاك بورد. في اللي كان مضيع اول او ما كان مركز لو ترجع بلاك بورد تشوف الفيديوهات باذن الله انه تكون واضحه، او يمكن يفايند اذر يعني يوتيوب فيديوز يمكن تشرح الفكره بشكل احسن. اوكي نقول اوكي Okay, so حياكم الله. So welcome again. So let's go and start and let's continue chapter 11, and we'll start with this slide. Where in this slide we will know something about what's called eutectoid and eutectic. And if you remember from previously, we said that in eutectic, when you have a liquid that will transform into two types of solids. So liquid will transform into two types of solids. طيب eutectoid, so عندك هنا liquid into two phases. Upon heating and upon cooling, you get these two phases will transform into liquid directly. Now we also we got to know about something about that's called eutectoid. Eutectoid, where you have a solid that transforms into two solids. So upon cooling, two phases can transform into one solid phase. Similarly, if you have one solid phase and you heat it up, that phase will transform into two phases. Okay, so that means in the phase diagram, one of the special reaction that we might, so in the phase diagram, one of the special reaction that we might have is the eutectoid reaction. So again, in the eutectoid reaction, we have one solid transform into two solid phases. Okay. This is very important because when you get into what's called iron-carbon system, where we have the iron-iron carbide phase. So we have iron-iron carbide phase diagram. In that diagram, we're going to have two important reactions. The first reaction was called eutectic, where you have a liquid transformed into two solids. And also you will have what's called the eutectoid reaction. And in the eutectoid reaction, you have solid transformed into two solids. Now, iron-iron carbide, it's a binary of all binary alloys, is one of the most important phase diagram, the iron-carbon phase diagram. Okay, so we have iron, and you start to introduce carbon to the iron, and interestingly enough, most of the practical applications, you need very small amount of carbon. Okay, so this is why practically all seals and cast carbon have less than 6.7 weight percent. Okay, so even if you add very small amount, 0.2, 0.3, 0.02% of carbon, all these small numbers are going to change the structure. And as we learned that in material science, if you change the structure, you're going to change the way the material is going to behave. In other words, you can change the properties of the material. Okay. Before we get into the iron-carbon phase diagram, it's very important to understand more about what is the iron itself. What are the crystal structures that iron might have, right? So if you have a pure iron without adding anything, okay, we know that the iron at room temperature, it's going to have BCC structure, body-centered cubic structure. Okay, BCC structure, we call this phase alpha ferrite, it has a BCC structure. Well, FCC structure, once you heat up above 912 Celsius. So above 912 Celsius, we're going to get what's called gamma austenite. if you keep heating up an iron, pure iron, okay, that also will allow the iron to transform to another phase, which is called delta ferrite, and which has also BCC structure. And then above 1500, the iron will melt. So this is very interesting. So if you take an iron and heat it up, the iron will transform from one crystal structure to another, and then it keeps this transformation from BCC to FCC, and then back to BCC, and then it melts. That means every time you're changing the crystal structure, you're changing the properties of the iron. Okay, so you're changing the properties of the iron. And also, every time you're changing the structure, maybe each crystal structure might have different solubility limits, right? So BCC might have, you can add amount of carbon that is different than FCC. Maybe FCC can accommodate more carbon compared with BCC, okay? So this is why it's very important to know this, that iron has different crystal structure, and that crystal structure, okay, they have different properties, and also they can play a different role when we're trying to have an alloy of iron and carbon, because different crystal structure might allow different solubility limits of carbon. If you look at the phase diagram over here, this is the iron carbide. We say that this is the y-axis where we have the temperature, okay? And if you look at the pure carbon, 0.8% carbon, you have to, sorry, pure iron, 0.8% of carbon. Okay, you get a pure iron, okay? And that pure iron in room temperature, it has a BCC structure. As you are heating up, what's going to happen at 800, at around 900 something, the alpha ferrite will transform to gamma austenite. And if you keep heating it, what's going to happen? It's going to transform back to a basic structure, what's called delta ferrite. If you heat up above 1500, then you're going to get the liquid form. I think this is now very clear because we have repeated this many times. Okay, now let's look at the x-axis. In the x-axis, you have the carbon weight percentage. How much carbon we're going to add to the alloy, okay? And this should start from 0 and end in 100% carbon. But because most practical application, you don't need to go beyond 6.7 weight percent. This is why in this phase diagram, you see that the percentage starts from 0 and end up in 6.7 weight percent. Okay? Because most of the steels, there are many types of steels and cast irons that we're going to learn, inshallah, about it in the coming chapters. You're going to learn about different types of steel and also cast iron, low carbon cast iron, we're going to talk about it, inshallah, we're going to talk about later. But the question here, what can we learn from this phase diagram? Well, first of all, before we start, if we say that from 0 to 100%, we're going to cut at 6.7, I would like to point out that at 6.7 weight percent, you have something very special. If you have 6.7 weight percent carbon and the remaining is iron, you get something that's called intermetallic compound. It's called cementite, iron carbide cementite. So iron carbide, and also sometimes called cementite. So that means this is representing 100% iron carbide. Yes, it is 6.7 weight percent carbon, but it's representing the 100% iron carbide. Okay. Okay. Now, if you look at how many solid phases you have in this phase diagram, we have alpha, we have gamma austenite. This is called gamma austenite. This is called delta. And rarely you're going to find practical application where you have you're using delta ferrite. Okay, so you have gamma, you have you have alpha ferrite, gamma austenite, and then you have iron carbide. These are the solid phases that exist, and here you have liquid phase. Okay, now if you look at this phase diagram, as we said earlier, there are two important reactions. We have first the eutectic, and why we call this one eutectic? Because liquid can transform into two solids. Just for your information, all of you, ya shabab, this is the third time I'm explaining this material. Okay. اللي ما هو فاهم إلى الآن أو ضايع وإلى آخره, please do your best, because this, if you go to the previous videos, we have explained this already twice before. طيب. Okay, so this is called eutectic reaction. We're gonna have a eutectic reaction over here. Oh, sorry, you have eutectic reaction as you cool below a eutectic temperature اللي هي 1148 سلسيوس. تمام؟ But at this eutectic composition اللي هو 4.30, a liquid gonna transform directly into gamma plus iron carbide. Liquid into iron, liquid into gamma plus iron carbide. Yes. Okay. So below eutectic temperature, any liquid you have, so if you have any liquid you have, what's going to happen? So below this temperature, okay, any liquid you have, either this liquid or this liquid or this liquid, what's going to happen if you cool below this temperature? Okay, what's going to happen between this composition and this composition? Any liquid going to transform into laminar structure of H, of gamma and iron carbide. Gamma and iron carbide, okay? Wonderful. But there's something special here, because if you have 4.3 weight%, you have the eutectic composition, all the liquid gonna transform into gamma plus iron carbide. However, if you're in the hypoeutectic, you are in a composition that is lower than the eutectic composition. So if you are in this region, what's going to happen? What's going to happen? If you are in this region, what's going to happen? Already part of the liquid transform into gamma austenite. This gamma going to stay as it is, as you cool below this eutectic temperature. Hello? Wonderful. So this is why gamma gonna go down as it is. Now the remaining liquid gonna transform into gamma and iron carbide. Okay. This is why you're gonna get two types of gamma at this point. You're gonna get two types of gamma. Gamma that already transformed before, and gamma that is transformed as a result of liquid transformation, liquid to gamma plus iron carbide. Okay. This is called eutectic reaction. This here you have eutectic. Yeah, hypoeutectic, here you have hypereutectic. Okay. Similarly, when we look at the eutectoid reaction, we have a solid phase that's going to transform into two phases, اللي هو alpha plus iron carbide. So if you cool down, the gamma austenite will transform into two solid phases, اللي هو alpha plus iron carbide. So this is a special composition. This is called eutectoid composition. It has 0.76. 0.76. This is called eutectoid composition. What is special about this composition? In all the gamma austenite, كل المادة الخام, the raw material that you have, gonna transform directly into gamma, gonna transform into alpha plus iron carbide. Okay. Now, as we learn from the eutectic reaction, that if you have a composition that is lower than eutectoid or higher than eutectoid, you're gonna have something different. You're gonna have something that's special. Okay. So if you are in this region, it's called hypoeutectoid. يعني you have composition that is lower than the eutectoid. If you are in composition that is higher than, if you have a composition that is higher than eutectoid, that is called hypereutectoid. معناته you have hypoeutectoid and you have hypereutectoid. Okay. Now, if you have eutectoid composition, all the gamma austenite will transform to one type of alpha, one type of iron carbide. It's called pearlite structure. Pearlite structure that has alternating layers of alpha plus iron carbide. if you have hypoeutectoid, that means if you have a composition that is lower than eutectoid, okay, you know that ايش اللي صاير يا شباب؟ You know that انه what's gonna happen انه هذه المادة الخام اللي هي الجاما جزء منها حيتحول إلى ألفا. So part of the gamma gonna transform to alpha, and that alpha will stay alpha as it is, even if you cool down to room temperature. Okay, واضح? Only alpha gonna stay as it is, even if you cool down to room temperature. And if you keep cooling down, من المادة الخام اللي باقي gamma. It's a raw material that's willing to transform, is not stable below the eutectoid temperature. This is why if you cool down, what's going to happen? قلنا if you cool down below eutectoid temperature, أي gamma باقي عندك, any gamma that's left can transform to alpha plus cementite. Okay, so that means if you are here, what's going to happen? How many types of alpha you have? You have two types of alpha. Pro-eutectoid اللي تكونت من أول اسمها pro-eutectoid alpha 1, and then you have the eutectoid alpha 2, and the other solid phase that you have is the cementite. Okay, similarly, if you are here, okay, and you cool down, now at this point, how many phases you have? You have two phases. You have alpha plus iron carbide. You have gamma plus iron carbide. Okay, so part of the raw material austenite transformed to iron carbide, and part of it stay as it is, gamma. And we said once you cool down below the eutectoid temperature, any gamma left can transform to alpha plus iron carbide. So that means if you keep cooling down to this temperature, below the eutectoid temperature, okay, you have iron carbide that's already formed before, واحد, and you have iron carbide that will be formed as the result of the gamma austenite transformation, طيب اثنين, and then third solid phase which is the alpha ferrite. Okay, and you can see that there is many similarity between the eutectic reaction and the eutectoid reaction, right? This is why it's called eutectoid. That means similar to the eutectic reaction. Okay, wonderful. Okay, now let's get deeper. Okay, now at 6.7 weight% carbon, قلنا إنه عندنا intermediate compound. It's called iron. It's called iron carbide, right? It's called iron carbide. أو أيضا, also we can call it إيش? We can call it cementite. Okay, we can call it cementite. طيب, carbon. How the carbon will be located inside the iron structure? Well, carbon will be as an interstitial impurity inside the iron. So it will not be a substitutional alloy. It will be interstitial alloy because carbon will be located only in voids between the iron atoms. Okay, so forms a solid solution with each of the alpha, delta, and iron and gamma cementite. This is very important, And when you add carbon to the iron, you can form solid solution, but you can form different solid solution اللي هم gamma, alpha, delta, and gamma. Alpha, delta, and gamma solid solution. Okay. Now notice إنه في alpha ferrite, في BCC alpha ferrite, you only can alpha ferrite can accommodate small amount of carbon, small concentration of carbon. The maximum that you can add carbon to the gamma ferrite, the maximum amount of carbon that you can add to the gamma ferrite, to the alpha ferrite is 0.022%. Okay, 0.022 weight%. This is the maximum amount of carbon that you can add to alpha ferrite BCC structure. Okay. even though small concentration gonna play a major role in the mechanical properties. It's gonna change the mechanical properties. Why? Because alpha ferrite itself, without adding anything, a pure iron is it's a ductile, it's soft, okay, and magnetic at room temperature and below. طيب. Once you start to add carbon, okay, once you start to add carbon, that start to little bit enhance its mechanical, improve its strength. طيب. فهنا because the alpha ferrite can only accommodate small amount of carbon. طيب. That's why its mechanical property is soft. طيب. Now if you go to other phase اللي هو عندنا الجاما اوستنايت. gamma austenite can accommodate up to 2.14 weight percent. طيب. so gamma ferrite عفوا alpha ferrite اللي قبلها alpha ferrite can accommodate up to 0.0 ارجعكم مره ثانيه هنا 0.022 weight percent. طيب. if you look at this diagram هنا لاحظ انه alpha ferrite if you add carbon you're going to hit the solubility limit. The solubility limit is تقريبا 0.022 weight percent. If you look at the gamma austenite, no, we can add more carbon up to 2.14%. Okay, so gamma austenite can accommodate more carbon. Okay, so this is why gamma austenite عندها higher maximum solubility of carbon. Alpha ferrite طيب has very it has no technological importance as I mentioned earlier. طيب. Now if you look at the iron carbide cementite, هذا الفيز اللي قاعد يتكون عندنا شفناه في الفيز diagram. تمام. الميكانيكال property حقته انه it's hard and brittle. معناته the more that you can add للalloy, the more that you can add cementite, the more the alloy become more hard and brittle and it's losing its ductility, right? So the strength of steel is enhanced by its presence. تمام. معناته this phase, an iron carbide phase, it's hard and brittle. Okay. Okay, let's get back here. So what we can see here, and we have gamma austenite, and gamma austenite once you cool down زي ما قلنا حيبدأ at this point to start to form alpha. If you cool down below eutectoid temperature ايش اللي يصير؟ الازرق اللي هنا الفاتح هذا يسمى برو eutectoid alpha اللي تكونت من اول، والباقي هذه المنطقة alternating layers هذه البيرلايت تتكون من مين؟ من alpha plus cementite. Because at this point you have alpha plus cementite. Here we call it hypoeutectoid. Here we call it hypereutectoid. Okay. Okay, wonderful. Okay, I think he is much clear. So that we have pearlite. So at this composition, if you cool down, المادة الخام اللي هي gamma austenite at point D start to transform to start to form alpha as you see. So you have gamma plus alpha, you start to form alpha. Once you cool down below the eutectoid temperature at point F, what you're gonna see? You're gonna see إنه هذه البرو eutectoid alpha زي ما هي موجودة. Plus إنه أي gamma كانت عندك gonna transform to alpha plus iron carbide in a pearlite microstructure. Similarly هنا we have in hypereutectoid. طيب you're gonna form pro-eutectoid alpha, عفوا pro-eutectoid cementite at point A. You have pro-eutectoid cementite plus إنه أي جاما كانت عندك حتحول إلى pearlite, alternating layers اللي تشوف what we see over here. Okay. Now, if sometimes in steel, beside the carbon you add other elements. يعني you have an iron and you want to make an alloy that has carbon and it has other elements that might enhance, let's say, the corrosion resistance, مقاومة الصدع. طيب. This is why we want to add other elements for the alloy. Now, what's going to happen if you add other elements? Well, what's going to happen is you're going to play with the eutectoid temperature. And you're going to play with the eutectoid temperature, you're going to play with the eutectoid composition. What does that mean? That means if you want to play, so this is the, let me take you one. This is called the eutectoid temperature. صح? So let's, so this eutectoid temperature 727, below which عندك أي gamma gonna transform to alpha plus iron carbide. Clear? Alpha plus iron carbide. Wonderful. Now, let's say you want to change this temperature, you want to play with it, you want to make it, at higher temperature or lower temperature. One way to do that, so you want to change this temperature, you want to have it, you take it up, or you want to take it down, the eutectoid temperature. What you can do, you can add alloys, right? You can add other elements other than carbon, and that will play with the eutectoid temperature. Similarly, if you want to play with the eutectoid composition, now the eutectoid composition for the iron carbide is 0.76. Imagine you would like to push it a little bit to the left or to the right. The question, can you do that? Yes, you can do that. You can play with that if you add other elements, because other elements are going to play in this phase diagram. I'm going to change it to, as you can see over here. Okay. So what is the eutectoid temperature? Well, the eutectoid temperature is, the eutectoid temperature, as we saw it earlier, is around 700 something. Okay. Now, if you start to add titanium, let's say with a small amount of titanium, what's going to happen with the titanium? لاحظ إنه the more titanium you add, the higher you can shift the eutectoid temperature line, البار, you can shift it up. Okay. Similarly with silicon, if you add more silicon, you can change the temperature, eutectoid temperature. You can push it to higher temperature. What's going to happen if you add nickel? Imagine if you want to lower the eutectoid temperature, then here we go. We have the recipe. What you're going to do, you're going to add nickel. If you add nickel, then at the end of the day, you can shift up the, you can shift the temperature to lower temperature. Wonderful. Similarly for the composition, if you want to play with the composition, okay, what's going to happen? You can add different, and you can see here all the alloys that you are adding over here is actually shifting the composition from 0.76 to lower composition, as you can see. Let's take the molybdenum here. Molybdenum, okay, the more that you add MO, molybdenum, what's going to happen? The temperature gonna decrease. After the composition gonna go to lower composition, the eutectoid composition. So it's gonna go from 0.76. طيب, it's gonna go to lower composition. Let's say 0.4. فين 0.4 عندنا هنا؟ فين 0.4 عندنا؟ So as you can see, if you add this amount, small amount, let's say of molybdenum, let's say around 1 weight%, okay, you can change it, the composition to 0.4 weight%. Okay, great. So this is going to take us to the end of chapter 11. So chapter 11, it was very interesting chapter because it introduced us what's called phase diagrams. Like how can we extract useful information from these phase diagrams? As you remember, we talk about that we can know something about how many phases exist, right? Also the weight% of each phase and the composition of each phase. We can know the composition by the tie rule. We can know the weight% by using the lever rule, and also allowing to produce a solid solution usually increases the tensile strength, decreases the ductility of the material, and binary eutectic and binary eutectoid allows for a range of microstructure as we talk about it. So we have perlite and we have pro-eutectoid, alpha pro-eutectoid, cementite, okay. So Now I have these slides in the Blackboard, so I urge you to go through the examples that you have over here. Okay, so you have an example over here that might reinforce the information that we talk about.